Algebra 3, it's Coach Jay. Hopefully you're having a great day today as we get started here. Hopefully everything has been a great day for you. I know the soccer team got a big win, and just a lot of good things came about today, so congrats to them. Hey, as we begin here, there's some things that I want to make sure we mention to you. For obvious reasons, there are a lot of you that did not come to class today, which I completely understand. But with that being said, just so we're aware, you're completely responsible for the material we went through over the last week. So be sure that you watch this podcast. Be sure that you come in the morning, both Wednesday and Thursday morning, and we'll go through that together as well. Also, if you hear my daughter, that she may be crying today. She's not had the best of days, but we'll deal with that as it comes. I love her to death, and again, if you hear her, I apologize there. All right, well, let's do this. Let's go through this study guide here. What I'd like to do is start from the back side and work our way forward, just to do something a little different. You'll notice from number 17 to 32, the ones that we're going to start off in, those ones are going to be non-calculator. So be sure you prepare accordingly for that, because on the test there also will be something very similar to that as well. Also, if you have any questions, be sure to text in there with the question number, and then we'll go from there. But other than that, what I'll do is I'll start from the back and move my way towards the front. And if you have any questions on that, feel free to stop me at any time. All right, without further ado, this is our last review podcast for our last test of the semester. Can't believe it's finally here. All right. Now, one thing we want to do when we look at something that is set equal to each other is we first understand that we're solving for x. That's important, because if we know that we're solving for x, we know that we're trying to isolate x. Well, there's a couple strategies. One of which, especially on the non-calculator side, is the fact that we want to get both of these bases to where they're equivalent to each other. So part of that is taking this and keeping the 4 to the 2x minus 1 and changing the 64 to 4 to the third power. So we're going to say 4 to the 2x minus 1 equals 4 to the third power. Now, as I look at this, I notice that the bases are the same. So I'm able to cancel those out, leaving me with 2x minus 1 equals 3. Well, obviously, as I continue, a lot of you already know how to solve this, obviously. We're just solving for x. And we obviously get something where x equals 2. Now, that's important, because what we could end up doing is plugging it back into the top and checking to see whether it truly is equivalent to each other or not. On this section, you could also use a four-function calculator. That may help you in going in doing some of this as well, but not a TI calculator there. All right, another one, number 30, is one that where it has 2 to the 3x minus 8 equals 32. That one too is another one. What we would do is change 32 to have the power of 2 to the, and I want to make sure I get this right, 2 to the 5th, okay? And that will be set equal to 2 to the 3x minus 8 here. And then obviously you cancel out and kind of go from there. I also want to come backwards to number 31. 31 is another one that may be a little tricky. The main reason why is because you kind of have to change both of them here. So for instance, this 27, we got to change that to be 3 to the third. And then obviously we'll have it to the x minus 4th here. And 9 will be 3 to the second. And obviously we'll have the x plus 2 on the outside. So what we would do is distribute 3 to the x, 3 to the negative 4, and 2 to the x and 2 to the 2. And all we'll do is just distribute across. So I'll have 3 to the 3x minus 12 equals 3 to the 2x plus 4. And then obviously we'll cancel, solve, and then that would be it. Now that's it for the one-to-one functions. There's another one here that says evaluate. This has 8 to the power of 8 log base 8 of 15. Now this one's a little bit tricky. The main reason why is because we've got to get this to where the bases of the exponent and the base could cancel out. Now they're the same, so we can't cancel. The only problem is that we have to get this 8 to where it's on the front or on the back side. so it's not on the front. So let's say I can move that 8. What we can do is move that 8 to the top to where we're left with 8 to the power of log base 8 of 15 to the 8th power. Now, since this 8 and this 8 are both bases and they're the same, we could actually cancel that out, leaving me with 15 to the 8th power, and we could actually leave that as is for that problem. Now, that's a little bit tricky because we really didn't go over one like that. If we have one like that on the test, then we might need to go through that one, but that's kind of the idea of what we would have going forward. The next one is number 27. In fact, let's do 27 and let's do also 28. Very similar. We want to try to get, is there something that we can try to figure out with this? Can we change this? What can we do? Well, anytime I say like on numbers 25 through 28, you could do one of two things. Number one, you could either just know it, or number two, if I were to set this equal to x, I could actually change this to exponential form to help me out. What I mean by that is this. What I could do is change this by shooting the 12 to the other side and changing this to what we would have an exponential form. Now, the x is not there on numbers 25, 26, 27, and 28. However, that 12, when I shoot it over, would be 1 equals 12 to the x power. So x, if I were to plug in for this equation, what could I plug in for x to be able to make it equal to 1? The answer would be equal to 0. X is equal to 0. On this one, we shoot the 4 over, and we get 1 over 16 equals 4 to the x power. But just like I did before, I want to get these bases to where they're alike. Over here was a little bit easier, but on this one, it might be a little bit tougher. So we could maybe change this around. You could kind of eyeball it. You could probably have a good idea. But I could actually change 1 over 16 to 4 to the negative second equals 4 to the x. The reason why is anytime I have a negative exponent, the same thing would be is to flip it on top of itself. So it would be 1 over 4 squared. We'd say 1 over 16. Okay? And so now we'd have the 4's cancel out, and negative 2 would be equal to x there. Negative 2 would be equal to x. And that would be my answer. And again, you can kind of test that out right there. But again, changing it to exponential form is definitely one way to do it. Another way to do it on number 26 is if I have log base 9 square root of 9. Again, I could set this equal to x and shoot the 9 over. But something that might be easier is if I see that the 9's are the same, and I could get it to where it's the same, I could make 9 or the square root of 9 the same thing as 9 to the 1/2 power. So if I have log base 9 of 9, that right there would actually cancel out, leaving me equal to 1/2. And so again, that would be number 26. All right. The ones where you change the log from log to exponential and exponential to log, let's look at 22. 22 is one where if I had log base 4 of 16 equals 2 versus number 24 where I have like the third root of 8 equals 2. Both are kind of the same idea except we're converting between it. So we want to go to exponential. This we want to go to log form. So in this one, in order to change it to exponential, we take the base of the 4 and we shoot it to the other side. We take the base of the 4 and we shoot it to the other side. All right, whatever you got to do, make up a song. I know Will was making up songs today. Maybe you can say, I'm all about that bass right there, you know, and I shoot the base to the other side and we keep this 16 the same. Whatever you got to do to make it to where, you know, you remember that, you know, you just got to do what you got to do. So 16 would then equal 4 squared. And that right there is how you change it to exponential. In this one, it's a little different because we got to try to give it to exponential first. This could be rewritten as 8 to the power of 1/3. Remember, the third root is the same as taking it to the 1/3 power. And then I could set it equal to 2. Now, in this example, if I could figure out a way where I could make these bases to where they're the same, that'd be a good, oh, I'm sorry, back up, I apologize. I was doing something different, I apologize. All I'm trying to do here is trying to get this to log form, right? So the base of the exponent, remember the base is the only thing that moves. So that moves to the other side. So I'm left with 1/3 equals log base 8, and then I keep that 2 right there. So again, the base is the only thing that is moving. If you can figure that out, it's going to save you a lot of heartache come test time on Thursday. All right. All right. I haven't gotten any text here. I'm actually going to check it out. Let's see how many viewers we have here. Actually have no viewers here tonight. I'm guessing that means that you get it. I'm hoping so. I'm hoping that means you get it. So let's do this. Let's go to number 20. On number 20, we have log base 5 of x plus 1 minus 3. And then I'm also going to graph another one just so that we're all clear on this. We're going to graph number 17. 17 is 2 to the x minus 3 power, and then plus 1 on the way outside. Now, a couple things to note here. First of all, let's take out our transformations real quick. One of the transformations we have is x plus 1. That means we're transforming to the left 1 and down 3. Okay? Left 1 and down 3. Now, with the x minus 3 here, we are going to transform right 3. I'm sorry, not left. Right 3, because we think opposite, and up 1. Okay? The reason why I circled that is that helps me to be able to see exactly what the transformations are doing. Now, in order to rewrite this, I'm going to just rewrite it as 2 to the x power, and over at the log, I'm going to do log base 5 of x, and then obviously equals y for both of these. Okay? Now, what can happen in both of these examples is we want to try to get it to where we get in a form we can actually plug into. The problem with the log is the fact that I can't plug into a log and get out anything that's even there. So what we're going to do is this. We're going to make it a little easier on ourselves. We're going to change this into exponential form. So we can do that by taking about the base, right? It's all about that base, shoot it to the other side, and we're left with 5. Remember, it's the base of the exponent and the base of the log. 5 to the y equals x. So I'm going to make my x and y chart here, just like I did here, okay? And when I make that chart, note that I'm going to plug in values for y, whereas over here, I'm going to plug in values for x. That's very, very important, okay? Very important. That's kind of the difference there. And again, I'm not plugging into this one, though you could. I'm really plugging into this one and this one here, okay? So I'm going to plug in -1, 0, 1, and 2. And over here, I'm going to do the same, except this time I'm plugging in for the y. So one thing to note here is that anytime we have a log, we will start with our vertical asymptote at 0, whereas the horizontal asymptote is going to be at a exponential. Remember, it's going to be an exponential like growth. And this is going to be kind of this way, the inverse of each other. So on this example, if I plug in -1 in for y, 5 to the -1st would be 1/5. 5 to the 0 would be 1. 5 to the 1st would be 5, and 5 to the 2nd would be 25. Okay, so as I graph this, I would have 1/5, -1. I would have 1, 0. I would have 5, 1. And as you could see here, you have a graph that looks something like that. Okay, so this graph looks something like so. Now, this is the end game, right? Because we have the transformations that are occurring. We're going to come to that in a second. Come back over here. 2 to the -1st is 1/2. 2 to the 0 is 1. 2 to the 1st is 2. 2 to the 2nd is 4. Now, one thing to note again, make sure on this one you note that I'm plugging in for y for my log because I changed it to exponential. And over here, I'm plugging in for my x. Let me put this over. Let's put this over on this side. There we go. Okay. So you kind of can see the idea there of what we have over on this side. Okay. There we go. Perfect right here. So now what I'm going to graph it. So I got -1, 1/2, 0, 1, 1, 2, and 2, 4. Okay. So I've got exactly this right here. Okay. So I've got my exponential growth graph going forward. Okay. Now the next one I'm going to do it in blue. Okay. So now I've got transformations. So now I've got to take this 3 to the right and up 1. Now remember this. If I move this right and left, we're talking this exponential, that does not change my horizontal asymptote. The horizontal asymptote is affected by vertical transformation. So it's kind of opposite if you think about it. So as I look at this, this thing's going up. So really, my new asymptote is going to go up to 1, okay? Because everything's going to move up 1, right 3. So if I take each of these points, I'm going to move it up 1, right 3, okay? Put it there. Up 1, right 3, up 1, right 3. And as you can see, you see a graph that looks something like this right here, the blue one. And the horizontal asymptote would be y equals 1. Now on this one, since it's a vertical asymptote is affected by horizontal transformation. Okay, so it's again opposite, right? So this is going to go left 1, down 3. So the fact that this goes down 3 does not affect the actual vertical transformation, but left 1 does. So this is going to be left 1. And each of these points are going to go left 1, down 3. Left 1, down 3. And so as I look at this graph should, and I apologize for the writing in the way, but it should look something like so. So the blue graph, again, what's in orange helps us get to what's in blue. Again, I drop the transformations, and then I can include that at the very end going forward, okay? So again, those were the things that we needed without our graphing calculator. I hope that was helpful for you. But again, that's one that you want to definitely look at and going forward there, okay? Alrighty. All right, so real quick, we're going to look at number 16, and we're going to kind of hit and miss here going forward. Just kind of hit and miss on some stuff here, but we're going to go on number 16. So 16 says the following. Now, there are quite a few word problems here. If you notice, there's probably, I think there's 6 of them. Yeah, 6 of them. That looks like a lot, but as you start reading these, you start realizing that they're really not tricky. That really all it is just trying to figure out what each variable represents and then kind of going from there. But it says this model is represented by the amount in pounds of a particular radioactive material is stored in a concrete vault, where X is the number of years since the material was put in the vault. So I would even put X is the amount of years, okay? All right. How much time will need to pass? Okay, time. All right, we'll see what we got here. How much time will need to pass for only 308 pounds to remain? Okay, so X is the amount of years. So we're trying to find how many years it would take for 308 pounds to remain. So 308 is going to be representative of the A here. So we're going to put this right here. Now this can be a little bit weird, right? Because now we're solving for X. How can we solve for X in something where where there's this E here, this is up in an exponent? How can I get rid of that? Well, first of all, let's do what we need to do. These are multiplied, so let's divide, okay? So when I divide that out, I get 308 divided by 500, okay? 308 over 500 equals e to the negative 0.00693x, okay? So what I'm going to do is kind of get this going here. 308 divided by 500. And we get 0.616, okay? 0.616 equals e to the negative 0.00693x, okay? So what can I do on this right side in order to get rid of this e? It's very similar to kind of ones that we'll come to later on. Well, the kryptonite, and that is ln, right? So the kryptonite is ln. My kryptonite, someone said today, was my height. That is, how dare you, okay? How dare you is all I got to say, okay? I can't control my height, so thank you very much, all right? All right, so as I do this, the ln and e cancel out, leaving me ln of 0.616. So I can divide by negative 0.00693 on either side. And once I do that, I get x is equal to approximately, let's do this now. Then we'll do the ln of 0.616. And then I'm going to divide that by negative 0.00693. And that answer is 69.91. Okay, 69.91. And it doesn't say how many, like what I round it to. So we can just do it to the 100th power. So 69.91 years is approximately how long it will take for it to reach then 308 pounds, okay? All right, so just again, make sure you write stuff out. If I didn't write that out initially, it might have been a little bit more difficult. But as you read the problem, write stuff out so you know exactly what to plug it in for, okay? All right, very similarly, 15 is very similar to this one. Again, this one was 16. You can use your calculator here. Make sure we note that, 1 through 16. But on this one, on number 15, note that A would then be equal to 5,799. And what you would be doing is solving for T in that way, okay? So you're trying to solve for how many years that is, again, after 2000, so you can kind of see what that's worth there, all right? All right, go to 14. 14 we did in class today, but still one that I felt like we needed to go over. Remember, there's two types of formulas. There's one that's A equals PE to the RT. There's also one A equals P times 1 plus R over N to the NT. This one is compounded continuously, and this one is compounded, well, it's compounded a number of different ways. It's numbers of times per year, okay? So if I say semi-annually, you would plug 2 in for N, right? Because 2 goes in for N. The amount of times you compound goes in for N in that instance. So in this one, it tells us a couple things. Let's note a couple of them here, okay? First, it says find how long it takes $28,000 or $2,800 investment. So real quick, we know that $2,800 is our P. Okay, we don't know what formula yet, but we're going to come to it. We're trying to find out how long it will take to double if it is invested at 7% compounded semi-annually. Okay, so there's the key. I did not hear the compound continuously. Therefore, the only formula that I'm going to go to is that second one. So I'm going to rewrite this just to see if I have anything here. So we know that the P is the initial investment. That's the $2,800 there that I'm going to plug in for P. The R is the rate. That's the percentage. If it's 7%, I could change that to 0.07 for that R. And if it's compounded semi-annually, that means that 2 is N. That's the amount of times I compound per year. So that would be that 2 there, okay? And again, it says how long. So we're trying to find how long, so we're going to find what the T is. Now, the only problem with this is what is A? There wasn't really a number there, but there was a hint. It said, how long will it take to double? Well, if I'm trying to double $2,800 or my initial investment, I know that I can only have one thing, and that's $5,600. So now what I need to do is very similar to what I did in the previous problem. I need to get to where T is by itself to be able to be solved for. So what we're going to do is we're going to divide by 2,800, not 28,000, 2,800. There we go. Boom shakalaka. When I do that, I get 2 is equal to 1 plus I believe it's 0.035 to the 2t power. And once I do this inside, I get 1.035, okay? Now, how can I get rid of that 2t? Well, there's a way you could do that. It's actually by taking the log of both sides, because think about it. If I can't change these two bases, the way to be able to get to where that 2t comes to the front is by taking the log of both sides. So once I do that, I get log of 2. I'll put it over here, equals, shoot the 2t to the front. So 2t log of 1.035. Now, since t is the thing that we're isolating, we can divide by 2 log base, or log of 1.035, getting t by itself. We do it to one side, we do it to the other. And so once I do that, I get log of 2 divided by 2 log of 1.035 to get my answer. All right, let's see if you can do it too. Log of 2 divided by, parenthesis, 2 log of 1.035. Okay? And once I get to that, let me make sure I got log of 2, 2 log 1. Oh, I forgot to do that. Let me do that one more time. So log of 2 divided by, parenthesis, 2 log of 1.035. Perfecto mundo. 10 years, about, it's 10.07. So really, so 10.07 years, approximately, is what we would have, is again what it would take for this investment to double, okay? All right, that was a really, really good one. Man, that was really good. Do this for me. Go to the front side. We're on the front page now. The two that I want to look at are two that, well, really we should have probably done at the beginning just to make sure we got, because that last one probably was a doozy for you. But if you got it, man, you are on the ball. I want to look at two of them. And actually, before I do that, just real quick, I want to make sure we touch base on one quick thing because it's stupid easy. Okay, don't want to miss stupid easy problems here. If I have 5 to the negative 1/3, 1.3, I could put in 5 caret parenthesis negative 1.3. Okay, I could also put that in as well and get that decimal out. Okay, that is definitely an option. All right, so just giving you a heads up on that. Now on this one, the one that is number 3, on this one, we want to try to solve this by utilizing the change of base formula. Now the change of base formula is a formula that we can use where if we can't get these two equal to each other, all right? So let's say that those are able to be equal and it's hard to find, we can use the change of base formula. So what we can do is do the log of the outside over the log of the base on the bottom. So it'd be the log over log, and the 59.1, the outside number goes on top and the inside number goes on the bottom. So it'd be log of 59.1. We call it change of base, log of 59.1 divided by log of 19. And I got 1.3854. I think it's, yeah, 1.3854 approximately. And that would be the value of that right there, that expression. Again, if I had like log of 3, 4, again, I can't get these to where they're the same. So a way that we can solve it is by doing the log of 4 divided by the log of 3. So that's just giving you that idea. Okay, this one's number 4. Very, very kind of same thing. In this example, we're not able to solve for the same base here of 9 or 3.9. So what we've got to do is be able to figure out something to where I could solve for this. And I don't think I have the previous one. But on the previous one, the problem where you did the, well, I think it was number 14, where you saw where it doubled, it was very similar. We're trying to get this x isolated, but there's no way to do it because the 9 and 3.9, well, there's no way to be able to simplify that. So what we're going to do is we're going to take the log of both sides. When I do that, since this is an exponent, this can then be shot to the front to get 5x log of 9 equal to log of 3.9. Okay? Now, how can I solve for x? Well, I could divide by 5 log of 9 on either side. And when I do that, I'm left with x is equal to log of 3.9 divided by 5 log of 9. Again, very similar to one we just did. We can do this anytime that we can't get 9 or 3.9 equivalent to each other. And also, anytime we're doing like calculator section, that's a hint that you're probably going to have to do this as well. So we're going to divide this by 5 log of 9 here. Perfect. To get 0.1239. 0.12. I want to make sure how many decimals is it? Oh, 2. So really just 0.12. Approximately 0.12 there. And that would be my answer. All right, so I'm hoping this is helping you. I know that right as we roll down here, number 9 you can throw out on your review there. Throw out number 9. We're going to do number 7 here and 8. 7, 8, 10, and I'm going to talk through 12, okay? So let's do 7 real quick. All right, on this one, we're trying to solve for x again. Again, I can't do anything with this because I can't break up log base 6 of 4x minus 1 unless I change it to exponential form. So what I'm going to do is I'm going to take 6, shoot it over to the other side to get 6 to the third on the right and 4x minus 1 on the left. Well, 6 to the third would be 216. Well, now what we can do is, well, we can solve. So we can add by 1, add by 1. I get 217 equals 4x divided by 4, and then we get my decimal and kind of go from there, okay? So 217 divided by 4, and that's how we get it. But the problem is what if we get one that does not, by the way, it's 54.25, exactly, 54.25. What if we get one like, let's say number 10? Number 10 is a little different because on this one, we're left with something where it has two values that have the same log, but they're split up. So I can't simply, by the way, there is no base, right? Well, there is. It's actually understood 10. So you may want to write that in if they don't give that to you on the test. Remember, ln has a understood one for e, okay? So as we keep going, one thing to note is that in this example, we've got to combine both of these together to make one log. So in order to do this, there's a rule that states that if I add two logs together, I can combine them by multiplying to be log of x times x plus 15 equals 2. Now remember the base is 10, so we're just going to put that there. So since this now has one log, very similar to this one, we can't solve with this. But what we can do is shoot the 10 to the other side, leaving me, let's distribute, x squared plus 15x equals 10 to the second power. Again, because I shot it, made it exponential form. Now, since this is 100, I subtract 100 to both sides, giving me x squared plus 15x minus 100 equals 0. Now, in factoring, we'll put x and x here. Two numbers multiplied get me to negative 100, but when added get me to 15. That would be positive 20 and negative 5. So when I set both equal to 0, I'm left with negative 20 and positive 5 as my two values there, okay? And again, just so you know, negative 20, it cannot be the answer. I can't get negative 20 because if I plugged it back in for x, log of negative 20, I wouldn't be able to have. So the only real answer would be 5 because that's the only one that produces a positive value, or that I can have a log of a positive value, which is one thing I can take there, okay? All right, so I know I went through that one quickly. We may need to look at that one together back when you come in the classroom, maybe even for a help session, either Wednesday or Thursday morning. All right, let's do this. Let's do this one real quick. Then we'll do one more, and then we'll be done, okay? On this one, again, the same type of deal here. We're trying to solve for x, and in doing so, 400 multiplied by e to the 0.05, or I'm sorry, to the 0.005x, we can't do. But what we can do is divide by 400 on both sides. When I do that, I cancel, leaving me e to the 0.005x equals 4. Remember the kryptonite for e. I got to be able to get that out of there. So we're going to take the ln of both sides. So when I do that, I'm left with 0.005x equals ln of 4. So when I do the ln of 4, and by the way, this would shoot to the front. Want to make sure of that. I know I haven't done that, but that would really shoot to the front, therefore canceling out ln of e there. So then I'll take the ln of 4, divide by 0.005, and leaving me with 277.26 approximately as my answer. So again, same idea. We're just making sure we solve, and again, using the kryptonite, using it to exponential or log form to be able to get x isolated. That's a lot of what we're doing in sections or numbers 1 through 16. Okay. The last one that I want to go over with is one that, man, some of us are going to have some problems on, mainly because we didn't really do a whole lot of these in class. However, it is POC easy. Okay, let's read this. Number 12. The function, and then it gives you this that you see right here, okay? Again, number 12. Models the average number of free throws a basketball player can make consecutively during practice as a function of time, where x is the number of consecutive days the basketball player has practiced for 2 hours. So x is the number of days. Remember that. Put that down. Tattoo it, whatever you got to do. After 206 days of practice, what is the average number of consecutive free throws the basketball player can make? Stop. 206 days is what we get. Well, since we know x is the amount of days, f of x the amount of free throws on average made, we're going to plug in 206 in for x. So we're left with 1 plus 1.5 ln of 206 plus 1. So again, once we plug that in and get it out, I believe we get 8.99, which should be approximately 9 free throws on average once you plug it in your calculator. Be careful. Make sure you do 1.5 ln of 207 and then add 1 at the very end, and we'll be okay. All right. All right, this was Coach Johnson tonight. Man, I'm all by myself here, but I am all about that bass. No trouble, okay? Or no trouble, whatever. I don't even know what the song says there, okay? But I just wanted to say how much I care about you all so much. And, man, can't believe that, seniors, this is it. I hope you all have a great night, and see ya. Have a good one. Bye.